Okay, so welcome to Unit 2. In this unit, we're going to talk about the biology of psychology and also take a look at the arguments of nature versus nurture. Again, very similar to the last unit, where some of you guys who are really into science had probably a little bit of advantage of there with the statistics and everything else. Some of you guys that are a little bit not pre-science, but have taken a lot of science classes, the biology is going to be very familiar to you as well, with us covering parts of the brain and the neuron and everything else. For those of you guys who do not have a strong science background, like myself, this will be taught in a way that it is what you need to understand about the science. If you're somebody who, the circulatory system, digestive systems, all these systems just really threw you off and whatnot, I'm going to try to explain this in a way that we only are concerned about how it affects psychology, and also hopefully in a way that you'll be able to understand it. And again, any questions, feel free to reach out to me. So with that, let's talk about biological psychology and specifically neurons and neurotransmitters is what we're going to take a look at today. The reason we're studying biology and psychology is because everything that we experience impacts how we act. Everything physiological is psychological and biological. They're all interrelated. Everything that I experience and I think and how I think about these things affect the way that I feel. And how I feel affects the way that I think. If I'm hungry, I'm going to be a little bit more angry with people. If I had gotten a good night's sleep, I'm going to do better on my test. So how I am feeling physically is going to affect me psychologically, and how I think psychologically is going to affect me physically. Everything psychological is simultaneously biological because our bodies are biopsychosocial. And also those around me are going to impact how I feel. There's certain people we're around that just make us feel better. And there's other people when we're around and they just make us stressed and we have stomach aches and ulcers and we feel worse. So it's very important that we take a look at when we're studying the brain, because the brain is part of the body. So it is biology. So biological psychology is taking a look at how our behavior is impacted with neuroscientists. The genes that we get from other people lead to our beliefs. There's very often, as much as I wish it didn't happen, I've got the DNA of my mother. This woman who was this 4'11" Romanian gypsy with a temper. And sometimes that temper can come out in me. Even though I don't think of myself as an impatient person, it's there. So again, that's going to affect how I act and do all these other things, and how people react to me as well, when sometimes that temper comes out. All right. So again, when we take a look at the brain, we're going to take a look at all these little different parts of the brain and whatnot, and how we measure it and do all these other fun things that go with it. All right. So we're going to start with the basics. We're going to talk about your neurons. All right. These are your tiniest of nerve cells. Single neuron axons that sort of take information in from the body. And as this pen hits my hand, the information has to come to my brain, and to tell my brain to close this and hold it, I kind of send it through neurons out to that as well. So we're sending messages out to our body, and we're receiving messages into our body, and we're communicating throughout our brain using all of these types of neurons, whether they're efferent, afferent, inter, whatever the case may be. We'll talk about that more in the next lecture. So to understand our thoughts, actions, memories, moods, we got to know how this communication system works. And there's many different types of neurons, but they're all pretty much variations of the same thing. This guy right here who's receiving information, sending it through, and sending it to someone else. It's just the communication system. Think of a neuron like a long extension cord. I've got to receive, when I plug it in, I'm receiving the electrical signal and sending it to the particular appliance. Because our brain communicates through electricity. There's electrical signals. I take what's going on in the world, I divide it into millions of little pixels and little bits of information, and then my brain has to put it back together. And getting that information from the world to my brain is done through neurons. When you're hearing my voice right now, you're taking these vibrations in the air and your ear is turning them into little electrical signals. When you see what's going on with this PowerPoint, you are taking little pixels and you're taking all these letters and all these little colors and everything, and you're breaking them apart, and your brain's got to put them back together, and it's done through the electrical signals. These signals could speed from 2 to 200 miles per hour, measured in milliseconds, but it takes a while to process. For example, if you ever played this game with someone, you take $1. All right, you take $1 and you ask somebody else to open up their hand. They open up their hand and you release the $, and they can't quite grab it. They can't. Yet if I do it with myself, and I release the $, and I catch it, it's pretty easy. It's pretty easy for me to do. Release, catch, release, catch, release, catch. It's harder for somebody else, because somebody else, when you're releasing the $, when you open up your fingers, their eyes have to see that open up, and then their eyes see it, goes to the occipital lobe, whatever, and then you got to put all those little pieces together, and then your brain's going, hey, they're opening their fingers. Oh, and I'm getting that from the sensory cortex. And so then I go, you know what I want to do? The parietal lobe goes, you know what I want to do? I want to close my fingers so I can catch it. So now your parietal lobe touches your motor cortex, and your motor cortex tells your hand, close your fingers, and you got to send that message down through here. And by the time you do that, the $'s already dropped. It takes a couple of tenths of a second. It's the reason why, if you ever play sports, the offense has the advantage over the defense, because the offense knows where it's going. The defense, it takes a fraction of a second to react. That's why we're always trying to anticipate. When you're driving in a car at 60 miles per hour, you think, oh, this is how the world is. It's not. When you're driving at 60 miles per hour in a car, you're actually anticipating everything that's happening. What you truly see, you're about 10 feet back. By the time you process it and everything else, you're 10 feet back. And then by the time you react to it, you're another 20 feet back, which is why alcohol, drunk driving, it takes even an extra moment to sort of react. So when we drive, we see our car, but we're actually kind of anticipating what's happening a fraction ahead of time. We're never truly living in the moment. There's this thing called chronostasis, which is this illusion that we're always predicting the future. We're always predicting a fraction of a second ahead, which is why when you look at a clock, there's a little blur. When you look at the second hand for the first time, it seems to pause and then go forward, because you're always predicting a future action in these particular things. And we'll be talking about that throughout. So again, what do neurons do? We take a look at this little message back here. Neurons transmit signals when stimulated by a sensory input or triggered by neighboring neurons. The soma is the neuron cell with a nucleus. So if this is the neuron right across here, this is the soma. This is the cell body. As with all other cells, the cell has to have a body. Now, the important part here is what I call the dendrites. The dendrites are what are taking information in. Again, if this was an electrical extension cord, this is the part that you're plugging in. So if these are your dendrites, there's other neurons that are connecting to it to send signals through the neuron and to the next place that it needs to go. So this is the connecting place where all these neurons are connected. Now, again, if I'm connected to one neuron, I could get the signal from that one neuron. But if I'm connected to 100 neurons, I only need the signal from one of them. So the more neural connections that I make, the more likely the signal is to get across. And this is why you'll hear me constantly say throughout the semester, making more neural connections. The more connections we make, the more likely the message is to get sent across to where it needs to go. All right, so these dendrites are receiving the signal to be sent to the rest of the body. Now, the axon is this guy right here. So as the signal comes across, the job of the axon is to receive the information and send it across to the other place. So again, if this was an extension cord, think of the long part of the extension cord. You know, this right here, pull this out. This is my USB cord. I plug this part in to receive the electrical signal. So the axon will just basically be like this. And then notice around the axon, and again, this could be very microscopic, it's a one-way road. When I plug this in to get electricity, it's only going this particular direction. It is a one-way road. Now, a USB cable obviously can go back and forth, but when you're getting electricity, you're just boom, and it's shooting straight across. And again, they could be microscopic in length to several feet long. Microscopic is one, or the thickness of, say, I don't have one, about the thickness of a pencil when you're talking about the optic nerve going back to the brain. Now, here's what's also important is that around, you don't see, when you take a look at this, you don't see the actual cable. What you have protecting around it is this little hard part. This is what is called the myelin sheath. The myelin sheath is the coating around it that protects it, that ensures that this message can come across here and is protected from outside things. So you have these fatty tissues on the outside protecting the signal as it goes across this white matter. Now, if this white matter is not there or becomes hard and fibrous with scleration, this is going to slow down the communication. It's going to make this not as flexible and other things. And if you don't have as much flexibility and you got, like, you know, you take this and you tie it into, you know, a knot, and you don't have the flexibility that you normally have, it's going to take longer for the message to go through. If you think of like a hose that has, you know, a hose that is twisted and it can't get the water across, it's the same thing with the myelin sheath. So if the myelin sheath is not protected, then what you're going to have here is the possibility of something like multiple sclerosis because the message isn't being protected across there. All right, so that's very important as well. Now, as the message comes across and it's being sent to the next neuron or the spinal cord or wherever its goal is to go, you come to these terminal buttons. And these terminal buttons, which are part of the terminals, their job is to send the message to the next neuron. So this message will be sent to another neuron, and then they will take the energy and sort of go forward. So these little bulbs on the end of this are what are going to shoot the message across these neurons. So again, this message will go across this way. There's your axon, there's your myelin sheath protecting it, and everything else, as the job is to shoot it to the next neuron. Okay, now as it is shooting from one neuron to the next, this message that goes across has what is called action potential. And the potential means that it has the potential to take the message and send it. It's not guaranteed that it's going to be sent, because if it doesn't make the jump from one neuron to the next, it's like it never happened. It never happened. So the more neurons you have connected, the greater the potential of the message getting across. The way that I like to look at these neural communications is to take a look at it as a row of dominoes. Okay, as I go from one neuron to the next neuron to the next neuron to the next neuron, what we're trying to do is we're trying to get the message across. If I come over here and I hit a domino, this is going to take the energy and go from one to the next to the next. And the energy is going to be exactly the same. This domino is not going to hit this domino any harder than that domino is going to hit that domino. The energy is going to come across. The message is going to come across completely the same. But if I remove one or two of these dominoes and I knock this domino over and that energy can't ever get to the next one, the message never gets across. So your action potential is just basically the ability of your message to get from one neuron to the next neuron. And the more neurons that are connected, the more that we have the possibility of getting the message there. This creates learning. You will hear me say throughout the semester, making neural connections. The more neural connections you make, the greater the possibility of learning, because the greater that the message is going to get across. When I'm first learning to speak as a child and making phonetics. I'm making more and more connections. I'm a little baby. I'm hearing the English phonetics. I got to make those more. So this is all creating learning. All right. Now the job is as the energy comes across, it's got to break through to the next one. Now, again, as much as I said neurons are connected, they're not quite connected. There's a little bitty gap right here. All right. So it's got to have the threshold to break from one neuron and microscopically jump over to the next one. And what's important about this is either the message gets across or it doesn't get across. I'm going to make up numbers here. But let's say that the message is a message of a 14. I am sending a 14 across. If I send it across and it makes it over here, it's going to make it over to the 14. It's not going to make it over here as a 6 because it was a little bit weak. It's not going to make it over there as a 17 because it was really strong and there were a lot of connections. It's either a 14 or it's nothing. Okay, so it's very, very, very important that the action potential comes across, makes it through the myelin sheath, and is able to jump to the next neuron in the complete status that it was when it went from the other one. And to make this jump right here is what we're going to call, and a bunch of graphics you can look at here, is the synapse. So the synapse is the little gap which gets the message from one neuron to the next neuron. And the more often you send this message, the easier it is to make this jump because you've done it so often. My ability to read the word between. Okay, I've got the neural messages in my eyes that have seen these sort of letters be made here and what these letters mean and everything else. And I've read the word between thousands of times in my life. So as a result, I just see a few letters and I immediately, it's between. It's easy for me to get that to my brain and bring it out of my mouth because I've said it and seen it so many times. Now, a little 4-year-old who is learning to read for the first time and doesn't quite know their letters is going b, b, betty, between, because they don't have those neural connections that I have. The more often we do something, the more we learn. When you first type, it's where the letter's at. But as you've typed again and again and again, you're just like, oh my God, where are these letters coming from? You don't know because you made that jump across the synapse so many times. But also when we get disrupted in the way that we normally do things, we have to reconnect. We have to relearn things. But that's also why relearning is easier than learning the first time, is because we already know how to make those connections. It's just reconnecting them. And now, in order to get the message from one to the other, something that can affect that message is what is called a neurotransmitter. So a neurotransmitter can affect the way that a message gets from one part to the other because they help transmit the signal between neurons. Pretty easy, right? Neurotransmitter transmitting signals between neurons. So when energy is released from one neuron to the next neuron, that energy is going across. And to assist that, you have these little different neurotransmitters, and there's many different types that we're going to talk about here. But these are very important when it comes to psychology, because let's take somebody with depression. All right, depression, really quickly, we'll get into this more details down the road. But somebody who has depression, my wife is someone who has suffered from depression for 40 years. Depression means that food doesn't taste the same. When you're in a depressive episode, a sunset isn't as bright, things like that. All right. So if I am watching a sunset, okay, and I'm a healthy person, I'm a mentally healthy person. But if I'm seeing a sunset, I see colors, I feel warmth, I see clouds, and I see beauty, and I'm in awe, and all these other things, and brightness, and all these things I'm taking in. So I'm taking in all these, I'm pixelating them down, I'm setting them in my brain as all these amazing things. Next to me is somebody with depression, and they see the sunset and they go, it's not as bright, it's not as warm, it's not as magical, but they're taking in the same stimulus. So they're taking in the same colors, they're taking in the same energy, they're taking in the same warmth, they're taking in the same whatever. So why is it to me beauty and color, and to them it's just, why when I bite into a sandwich, it's like, oh, the lettuce, the tomato, the little bit of mustard, the little saltiness of the salami, and it's all great and combined. Yet somebody with depression bites into the sandwich and they're like, yeah, it's food. And it doesn't taste as good as it did before. And sometimes it's because their neurotransmitters are off. Their serotonin levels are off. Their dopamine levels are off. Their endorphin levels are off. Whatever the case may be. So, and then there's times where we have enough, and there's times when we don't have enough. There's times when we have too much. And this is why we need, sometimes people in depression, anxiety, whatever, need to take medication in order to impact how these messages are being sent from one neuron to the next. And we'll be covering that throughout the semester. Let's take a look at a few neurotransmitters that we'll be looking at throughout. One is called dopamine. Dopamine is voluntary movement, but dopamine is also pleasure. We like it. It's excitement. It gives us a rush. We want that hit, that excitement. That cocaine has that same effect of dopamine. It stimulates us. It's fantastic. It's one of the reasons why you guys are so addicted to your smartphones. And a lot of you guys can't take your smartphone and keep it off your desk. You have to have it there because at any moment it could light up. And think of the excitement when your brain sees the phone light up and there is a message. Think of the excitement that happens, that little bit of a rush. Oh, I'm going to get news. I'm going to get information because we want to learn. Learning is exciting. It gives us a dopamine hit when we learn. You know, you get a text message and you look at it and you go, oh, Susie broke up with Johnny. Oh my God, Susie's available. You know, I got this information. I was first. Nobody else told me this. I know before anybody else. And there's a rush that comes to our brain. When you play the game and you get to the next level that you never did before, now you learned how to beat the game. There's a rush that comes with it. When somebody is texting you and they have that little dot, 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 which they've put in there because it gives you a dopamine hit of, oh, what's coming, and that anticipation of that pleasure of that news. But when it's not news, it's not as pleasurable. You know, when you get the text message, Susie broke up with Johnny, you're like, oh, man, I already knew that. And we're upset because we're not getting that hit, you know, and that's the problem when we get too much dopamine is when people get addicted to drugs, you know, because what happens is you have a withdrawal. You're never as high as your first high. You know, people who, if you do cocaine, let's say that this is your normal, this right here is your normal level of producing dopamine. Your body produces dopamine at a level of this, but you're like, this isn't good enough. I want a high, I want a hit. So you take a drug like a cocaine, all right, a cocaine. So you take cocaine and you because you want that high to bring it up, but then your body's going, whoa, what are we doing way up here? You know, I was producing this much dopamine, but suddenly we're high and we're up here. I should produce less to bring us down. So now your body's down to here and you're like, oh my God, I got to take a little bit of coke just to get normal. But if I want that high, I got to take a little bit more. Well, I'm going to produce less. I got to take a little bit more. I'm going to produce less. I got to take a little bit more. I got to produce less. Well, that's it. I'm spending too much on coke. I can't do this anymore. I'm losing my job. I'm losing my family. I'm going to stop. Well, now I'm in this withdrawal because I'm not taking what I used to take. You're never as high as your first high. You're never as drunk as your first drunk because these drugs that we take, we're messing with our body chemistry, especially when we don't know about them. You know, the stimulation of the vaping, you know, it's addictive because our body depends on it because our body stops producing what it may naturally produce. Now, again, prescription medication, if you're naturally not producing enough dopamine, you need a stimulant to do that. But that's what doctors are for and everything else. Okay. Some little things there on dopamine and what parts of the brain it affects if you want to take a look through those. All right, now let's talk about serotonin. We talked a little bit earlier with depression. Serotonin affects aggression, hunger, sleep, arousal, and mood. Think of mood, my serotonin, the tone of your body, the tone of the way that you see things. Prozac, other antidepressants, their job is to raise serotonin levels that are not there. Also, it can reduce aggression when we do this. Low levels are tied to impulsive aggression because people can't sort of take care of those particular things. Too much testosterone, not enough serotonin. And this is why not all depressed people show depression in the same way. You know, women are diagnosed with depression more than men, but it's because women's symptoms are different, where they tend to be a little bit more withdrawn. A lot of times guys with depression will act aggressively, but we're like, well, that's not depression. Sometimes it is. There's not a lot of reflecting when lacking serotonin because you can't get to the emotions and everything else. Increasing the levels of serotonin does have an impact on impulsive behavior of teenagers, and it helps it. Not as much on adults because teenagers, the frontal lobe your impulse control is already sort of not there. So any help would be great. Abnormal levels of serotonin can contribute to depression, OCD, and things like that. Natural serotonin boosters, people that are going through depression, reducing your sugar, going out into the sun, positive thinking, exercise, all these things, which, by the way, seems like just an incredible, oh, you're depressed, go to the gym. You're depressed. It takes enough energy just to talk to somebody, let alone go to the gym. I'm mentally healthy, but that I can't get to the gym. So just go for a walk, just exercise, just go out in the sun. It's easier said than done when you're dealing with somebody that has depression there. But serotonin, the tone, can really impact that. Norepinephrine, which is the neurotransmitter equivalent of the hormone adrenaline. Okay, adrenaline is a hormone. It goes through our endocrine system. We'll talk about that in a couple of lectures from now. But norepinephrine is just that release of intense energy in the brain where we can work a little bit faster. A lot of times in times of stress, when we're in that fight or flight stage of, is this stressful? Is it not? How do I resist? How do I deal with it? The norepinephrine allows our brain to work a little bit faster than what it normally would. It makes these connections quicker. Acetylchlorine, this is muscle actions of skeletal muscles. This contributes to attention, learning, memory, making sure that we're getting the memories from one place to another. A lack of acetylchlorine can lead to temporary paralysis, which sometimes a snake bite or whatever else can do. People that have degenerative diseases of walking or getting to memories like Alzheimer's, a lot of times there is a lack of acetylchlorine that is there. Studies show that nicotine can stimulate the release of these neurons. But again, if you use nicotine, which is in vaping, by the way, to stimulate this, when you stop vaping, you don't have that stimulation, and then your body stops naturally producing it even more because you're dependent on this outside thing coming in. Gamma aminobutyric acid, this serves inhibitory functions to block messages that can be implicated in eating, sleeping disorders, the release of melatonin, which is a hormone, which we'll talk about a little bit later on. A lot of times to treat anxiety disorders, sometimes Valium will be put in there to sort of mimic this particular neurotransmitter that we might be lacking. Endorphins, which are very, very, very well known as the runner's high or whatever. These are the painkillers. These are the painkillers that we have because pain is completely mental. All right. If I cut myself, I don't realize I cut myself, I may not feel it until I look down. I go, oh my God, there's a cut. It hurts. Because pain is mentally produced by us. Pain is good because pain tells the body that something's wrong with it. So, take care of that cut or whatever. Now, sometimes we don't have time to deal with the pain. You're in a basketball game. You twist your ankle in the first quarter, but there's still 3 quarters to go. You don't have time to deal with it. So the coach tapes it up and the endorphins are released to block the signal. Where normally these pain signals are up here, what happens is the endorphins block the message from getting to the next cell so that I don't get these signals of pain. But as soon as the game is over and the endorphins wear off, you're like, oh my God. This is why some people who are runners, especially in long distances, running is kind of stupid. And when I say stupid, to run 24, 26 miles of a marathon, that's not natural for your body to do. So the first mile or two, your body's like, ow, pain, this really hurts. But then after a while, your body's going, what? We're going to keep running. You're not going to stop. Okay, fine. I'll take care of this for now. And it starts to release these endorphins to deal with this particular pain. And then when the run is over, the pain sort of hits you and whatnot. Sometimes when we have pain, we don't have enough endorphins to take care of it. So a lot of times we'll take pain medication. Now, again, pain medication is possibly the most addictive, overprescribed, overused drugs that there possibly are. Because when you take pain medication for an injury or whatever the case may be, your body's going, oh, I don't need to produce endorphins because I'm getting these artificial endorphins coming in. And then you actually get somewhat addicted to this pain medication. That's why you always have to be very, very careful of only taking pain meds when you need it. not just because you want to take them. All right. So you got some other stuff here: dopamine, serotonin, oxytocin. That is a hormone, which we'll talk about in a little bit. But other stuff there, if you want to take a look at those neurotransmitters. Last thing we need to talk about to wrap up this unit, though, is drugs and how do these drugs impact neurotransmitters. Okay, so the neurotransmitters are signals going across. Now, a lot of times the issues that we have is because we either have our neurotransmitter levels are just not at a healthy level. I either have too many of them or I have not enough of them. So in order to take care of this, there are two types of prescription medications when it comes to these neurotransmitters. They are either agonist or they're antagonist. An agonist is something that says you do not have enough of a neurotransmitter. So this is a prescription drug that is given to you to deal with a boost to you don't have enough. You're somebody with depression, you don't have enough serotonin. Here is a drug that will mimic serotonin. So an agonist is something that you don't have enough of, so it's creating it. An antagonist means that I have too much of a neurotransmitter. So the job of a drug that is an antagonist is to block the signal from getting to where it's supposed to be. For example, somebody with schizophrenia, they have illusions, they have hallucinations, they see things that the rest of us don't see because they have too much dopamine, too much stimulus. So what they would do is they would take an antagonist, and the antagonist would block the dopamine so that they don't have those hallucinations anymore. Okay, so some other stuff there, some reviews on there, more you know, if you want to take a look at that stuff going through, but that should wrap us up for this particular lecture. Next lecture, we will talk about the nervous system.